Hello, everyone. It's a pleasure to be here. Before I start, I'd like to thank the organizers for setting up this webinar and inviting me for delivering this presentation. I think in the next half an hour or so, I will try to give you a broad perspective on different types of HTS assays and readout modalities, general conditions that are amenable for screening, and how to systematically evaluate assay performance. And along the way, I'll point out a few possibilities for improving suboptimal assay conditions. Some background about myself and Pivot Park Screening Center. I'm a biotechnologist by training with background in biomolecular and cellular screening and currently Director of Drug Discovery at Pivot Park Screening Center. PPSC is a contract research organization based in Os in the Netherlands, and we specialize in early drug discovery services to big pharma and biotech companies. And our services focuses on assay development, medium to ultra high throughput screening, and hit to lead biological profiling. And we are really proud to be part of the European Lead Factory as partner and contribute to the hit finding efforts at ELF. This is a depiction of our fully automated UHTS platform that consists of 3 pods with a robotic arm in the center of each pod. The pods are interconnected with a conveyor belt with a traffic cup in between. And the instruments are oriented around the robotic arms on dockable carts, which means depending on the requirements of a given HTS campaign, we can flexibly plug in the right instruments to the system. The additional advantage of this is that with these dockable carts, you can keep the platform up to date. The latest upgrade we have been doing on the system is including the RapidFlex for label-free multi-TOF mass spec readout. And the system has the capacity to have up to 2.5 million compounds online, and we routinely generate 100 to 200,000 data points per day. And to achieve this throughput, we have general conditions to consider an assay HTS amenable. Preferred conditions such as use of 384 or 1536 well plates, homogeneous and endpoint assays. Although minimal washing steps, it's still acceptable because we do have a few blue washers in the system, but assays such as standard ELISA are not compatible because of the many washing steps. Also, fast kinetics, such as calcium kinetics, membrane kinetics, is also possible. This is, for example, an assay that we could run using flipper-based readouts. We require robust assays that are characterized by a number of assay parameters, such as Z prime, signal to background, coefficient of variation with a specific cutoff. And I will further discuss this in the later slides, because in a typical HTS campaign, there are massively parallel procedures carried out over many hours. We need short incubation times and also stable readouts and reagents. As compounds are dissolved in the MSO, assay reagents need to tolerate the MSO in the buffer or in the wells. And for cell-based assays, usually we need mycoplasma-free cells and freedom to operate using these cells, because some of the cell lines that are commercially available are IP protected. For some biochemical assays that we run, we need to have minimum of 80% purity of the protein to really guarantee high quality results. And last but not least, doing large-scale screening is inherently expensive, so the cost per well should be affordable enough. So now in many cases for novel drug targets and assays, there are no readily available miniaturized assays for screening. And in the next slides, I'm going to tell you about typical frameworks to go from a test tube to multi-titer plates. Although in many academic labs, using 96 well plates are still common, but to a lesser degree, 384 well plates, and also less than that, 1536 well plates. There are key questions to consider before putting an effort in setting up your assays. These questions are as the following. Are we trying to inhibit or activate the target? What types of hits are we looking for? Allosteric hits or orthosteric compounds? What function of a target are we trying to modulate? Is it an enzymatic activity? Is it an interaction between 2 or 3 partners? Are we looking to inhibit a certain localization? The answers to these questions would determine what kind of assays to employ, but also how to tune and optimize and tailor your assays. The next question is whether the assay, what kind of HTS assays are amenable for screening. I think I previously discussed that a little bit. It's important to really be sure what type of cells or biochemical setups to use, and one can think of different scenarios about that, and I will briefly discuss this in the next slide. It's important to know the physiological conditions in which the target is functional. For example, what protein states are required? Is a target active as a monomer, as a homo or heterodimer, or whether you require full-length proteins or you're trying to inhibit, for example, a certain domain of the protein target. Also, the next question is what kind of readouts are available, and that has in one way one needs to think about also the costs of those reagents, and it's very important to also think about hit triage cascades. So in order to find basically compounds that are validated, and hit triage cascades basically contain deselection, orthogonal, and selectivity assays, and also biophysical assays. Once we have these assays in place, of course, we want to scale them up, usually to 1536 well plates, and we need to make sure they meet a certain quality in order to be able to do HTS campaigns. So there are mainly 2 types of HTS assays. There are mainly 2 types of HTS assays: biochemical target-centric assays that require purified proteins or crude cellular lysis that contain the target. Typically, these are used for enzymes, receptors, protein-protein interactions, or protein interactions with nucleic acids. And we have also cellular assays that are employed for both target-centric but also phenotypic readouts. Typical readouts for cellular assays are transcriptional readouts based on reporters, for example, second messenger levels, protein interactions also based on reporters, protein localizations, upregulation or downregulation of protein levels, as well as endpoint phenotypic readouts. Obviously, there are inherent pros and cons for both types. Biochemical assays are less physiological, but there is a lot of freedom to tailor different conditions in these assays, and cellular assays are more physiologically relevant and are better suited for example, certain target classes such as GPCRs or ion channels. Or you may actually need an active cellular machinery for that particular target and hit finding. There are many variables to think of and also adjust when we set up biochemical assays. We typically have different buffers to control pH, variety of options for salts. These could be mono or divalent salts. And we typically have detergents, mainly to keep everything in solution. Reducing agents, some proteins requires some reducing agents to be active. Chelating compounds, for example, for stopping an enzymatic reaction, perhaps you need RNA inhibitors if there is some RNA substrate in your assay, different types of dyes for measurements, but also some of the test compounds themselves could be autofluorescent. The target itself and perhaps conjugated or in combination with lipids if there is a need for the protein to be membrane bound. Test compounds that also sometimes come with trace amounts of impurities from the synthesis part. There are solvents, substrates, co-substrates, cofactors, and in the cellular assays, usually serum and basically the gross medium and also the air around. Here I'm showing you an example of an HTRF assay to measure the interaction of two proteins in 6 different buffer compositions, plus minus different salts, reducing agents, BSA, detergents. On the x-axis is the concentration of different proteins, and y-axis is the Fred signal. You immediately see that saturating the system with protein doesn't necessarily give you the best signal. So you can see that optimal conditions could be achieved by using slightly lower concentrations. Also, clearly you can see that there is the buffer composition can very much influence the kinetics of the assay. So it's important to profile different assays and really upfront know what is required for, let's say, this is a protein-protein interaction, but other targets may require other conditions. Here is a heat map of signal from an assay plate that doesn't have detergent in buffer. So these 4 columns are the positive controls, and this is titration of a reference compound. You can see a lot of well-to-well variability in the signal. This is typically for sticky proteins or aggregation of materials in the buffer. And you can really avoid this usually with very low concentrations of detergents. There are many readout modalities that one could use. Conventional multimode readers cover many of them, and we can also measure fast kinetics, such as membrane potential and calcium fluxes with flipper-based assays. And as I mentioned previously, we recently can also do label-free MALDI-TOF readout in 1536 well-plate format. Here I'm showing you results from 2 assays, assay readouts based on the same target, perturbed with a selected set of typical assay interfering compound classes. These are aggregators, chelators, colored compounds. This is a DMSO control, fluorescence, luciferase inhibitors, reactive and redox compounds. And these are typically the kind of compounds that come up in a lot of assays as false positives. And if you compare it to a TR-FRET assay, you see that compared to the luminescence one, none of these liabilities are out there. And this assay basically just picks up drug-like molecules. So this doesn't tell you necessarily that universally TR-FRET assays are better than luminescence assays, but the point here is that this is very much context dependent, and it's good to know your assay liabilities before going to screening phase. To this end, we have to, in order to find high quality hits after the primary screen, one needs to have appropriate hit triage assay cascade in place. This is usually based on theoretical or empirically found liabilities of the primary assay. Typical follow-up assays are, for example, deselection, or also called counter screen assays that basically it's a process to get rid of anything that is interfering with your readout technology. Orthogonal assays, basically using the same target, but with another readout to confirm the actives. Selectivity assays may be required to get rid of any compounds that have off-target selectivity, and also biophysical assays that are absolutely crucial to characterize target engagement. Here on the left side, I'm showing you the primary active rates based on a particular cutoff from 72 full dex screens we have carried out within the first phase of ELF on a variety of targets and based on using different readouts. And 1% active rate from screening 500,000 compounds means you have 5,000 active compounds, and many of them are usually false positives. And for this reason, on the right-hand side, you can see that we have employed many follow-up assays as well, even more than the primary assays. In the rest of this talk, I'd like to focus on the conventional frameworks to evaluate assay performance. When we evaluate, for example, dynamic range of the assay, we want to know if there is sufficient separation between the positive and negative controls. With robustness, we want to know if the assay can cope with technical and biological variations present in these assays. With reproducibility, we want to assure that there is minimal well-to-well and plate-to-plate variation. And performance, and with performance, we can basically make sure that the assay is able to pick up statistically significant data points. So typically, in a primary UHTS campaign of large compound libraries, basically we are testing every compound once at a single concentration. This is typically 10 micromolar. It's vital that the assay is reliable enough such that this single test is a true representation of the activity of the compound. And we also need to be sure that each plate in the screen is valid and that data is comparable across plates and experimental runs. Therefore, compounds typically their activity is normalized around the max and min control. So your minimum control could be a DMSO, and your max control, as an example, could be a reference compound. And this allows us to compare data across plates and experiments on a common scale. The compounds in the presence of the typical errors may actually go beyond your max and min, but in some cases, actually your reference compound may be actually less potent than the hit that you're finding. And in other cases, maybe you're looking, for example, for an activator, but in the library there are compounds that result in inhibition of your target. So reproducibility is also an important aspect. If we have, let's say, a cutoff of 50% and we test the compound on one plate and you have 90% activity, and on another plate you have 40% activity, that means that identifying hits is going to be challenging because of lack of reproducibility. Also, here I'm showing you basically an assay window. You would imagine this is a large assay window and it's a reliable assay, but it's also very important to take into consideration the variation. And looking at basically the assay window alone could be misleading in presence of variation. Therefore, a common parameter to evaluate assay performance is Z prime or Z factor. which takes both the standard deviation of your controls as well as assay window into consideration. And here you can see the distribution of your max effect controls and distribution of min effect controls and the separation between the two. And in general, a good assay has a clear separation between the tails of these distributions, and you want to have a higher than threefold separation band. Of course, you don't want to always look at these plots. There is a way to have just basically a single number for calculating z factor. You can or z prime. You can use this equation, and the highest number you could get is a 1. That never actually happens. But what you want to have for an HTS amenable assay is a value between 1 to 0.5. And this means that there is a very large separation between assay window. Lower Z factor values are also fine in certain cases, but this will drastically reduce the possibility of finding weaker compounds with less efficacy. And essentially anything around 0 or below 0 is not appropriate for large-scale screening in single shot assays. We also need to evaluate the coefficient variation, so basically the well-to-well variation. Ideally, we want to have an assay that has a CV below 5%, but below 10% is also acceptable. Here I'm showing you some examples of how you could set up 4 different plate formats, basically with your min controls and max controls organized in different ways. And by doing this, you can systematically change different assay conditions and see whether you can basically reduce your coefficient of variation. There are multiple things that you can try if your CV is too high. An easy one is actually just by switching to different plate types. Here you see an example of a binding plate and a non-binding plate, and this is basically data from each well, and you can see that in this one you have a lot of variation, and switching simply to another plate reduces that variation without changing anything. So this may be, for example, due to stickiness of the protein. Other points to take into consideration to reduce such variations is looking at different batches of proteins or different protein vendors, or slightly modifying the conditions in which protein is produced. Checking different readout reagents, batches, fine-tuning temperature and incubation times, testing stability of the readouts and the reagents. Maybe even different colors. So depending on what is the readout, different colors may give you a better dynamic range and less variability. Typically using liquid handling instruments and dispensers, if you have access to them, will drastically improve assay parameters. And also, depending on which plate you're using, it's very important to benchmark that reason and that reader and benchmark it for that particular plate. Also, it's a very simple thing to do, but minimizing the dispensing steps usually reduces the variation in setting up assays. For the case of cellular assays, if you have plate effects in cellular assays, you could try to shorten incubation times, use frozen cells if possible. You can adjust seeding density. You can really try to seed homogeneously. Dispensers usually help with that. You can adjust different volumes and concentrations of the detection reagents. Perhaps if none of that works, switching to alternative readouts or trying to use clonal stable cell lines. These usually help to reduce the biological variation, and switching perhaps to a different cell line or growth media, and also improving incubation conditions. So as a take-home message, I really recommend you to know your targets well and acquire all the information available in the literature on your target, and ask the right questions when it comes to picking the right assay and the right conditions. You need to have a sound biochemistry, so look at kinetics, measure Km values or Kd values, make sure that the assay is linear, and also you're reading out your endpoint assay in the linear part of the kinetic curves of assays. Use robust statistics to evaluate assay parameters, and you can improve assay conditions by those variables that I mentioned. And I showed you also some examples that every target assay readout combination is unique, and it should be treated as such. And it would be very good if you already identify assay liabilities and think of what triage cascade you might need to employ down the road to identify high quality leads. And if you have any questions, we are very happy to help you during assay development. Feel free to get in touch with me directly or with colleagues at the Ligature. So the whole concept of assay development is very broad, and I don't think in half an hour one can cover everything. I really recommend this public resource. You could really use it as a cookbook for setting up assays. There's a lot of useful information and tips and tricks on how to set up assays. And with that, I'd like to thank my colleagues at PPSC and also our partners within the European Lead Factory Consortium. It's really a pleasure working in this consortium, and I'd like to thank you for your attention. And I'm happy to take any questions.